Good night, everyone. I'm Pranay J. Reddy, a PhD student here at the Champalimaud Foundation.
And I am Anamaya, a physician working in psychiatry and a PhD student at the Neuropsychiatry Unit of the Champalimaud Foundation.
We will be your hosts for tonight, and we are so glad you're all here. So we'd like to formally welcome you all to the R series, and we hope you have a memorable evening.
So R is back from a small pause, and we are extremely glad to be here with you in this lovely auditorium. To provide some context about our initiative, R is the Portuguese word for air because we believe that science, like air, should be free and available to everyone. A ciência está no ar, respire conosco.
Science is in the air, breathe with us. We truly believe that motto, and with that motto in mind, we thought of focusing on a topic which is pretty global, has a global impact, but is embedded in every corner of our lives. Well, spoiler alert, it's artificial intelligence, or AI for short.
Along with the exponential technological development over the last decades, AI has started to influence a wide range of human activities. From science to art, from education to healthcare, from politics to employment, AI has really started to have an important impact on the way we live. The story of AI revolution is the latest of a series of technological revolutions and will certainly not be the last.
Completely agree, Anna. It's been part of our human history. We had multiple changes in lifestyles. Think about it. We go back to the discovery of fire, and then fast forward a few millennia, we get to the Industrial Revolution, then the Digital Revolution, which has now led to our world living in a bunch of algorithms, right? And that has now led us to this current moment, revolution in AI. So I think it's important as we're going through this revolution to actually understand some fundamental concepts of AI. So we in the art team, with this thought process let us bring a series of events which includes the past, the present, and the future of AI.
So tonight, we will talk about the past of AI, or rather the roots of AI. And to do so, tonight's event will incorporate three parts. First, to start truly digging into AI, we will have a dialogue on what intelligence means, where Pranay and I will talk, discuss, and explore this concept. Then, Tiago Marques, an in-house scientist, will help us understanding the story of AI research, focusing on important concepts and on the way neuroscience and AI research have been intertwined with each other.
And finally, we hope to combine some of the things we learned in these two concepts and bring about an AI creation of sorts, Leslie. We'll introduce you to Leslie, but the whole point of having Leslie is to bring us through the past milestones of AI, which has led us up to this very moment. So, many things to look forward to. I hope you all feel the same way. Let's get started. I'm pausing for dramatic effect. I think I've waited way too long. But as Anna suggested, let's dive into artificial intelligence. I think we start with the basic question, how do we understand artificial intelligence?
Yeah, well, if we really think about it, the name is rather self-explanatory, right? It has two words, artificial and intelligence. And while artificial means something that was created by humans, well, intelligence, that's a bit trickier. But what do you think, Pranay? What do you think intelligence is?
I mean, as a guy trying to study neuroscience, yes, I do agree, answering intelligence is a bit tricky. But let's start with an example. I mean, us. By us, I mean humans. We are intelligent.
I'd
right?
like to think so.
I mean,
yeah,
I think we can firmly say we are intelligent. I mean, come on, we built cities. Look at that architecture. That's Lisbon skyline, right? That's beautiful. And then we went to the moon. I'm pandering to the Portuguese audience. We went to the moon, and it's in outer space. And we also have this incredible processing power in our pockets, mobile phones. And also, we have created timeless masterpieces such as the Spider-Man meme.
Yes. Or historical paintings describing our own creation, for instance.
I mean, here's the thing. Both of them are pointing at each other. It's just art is subjective, so I prefer the Spider-Man meme. So there you go. I think we can agree to disagree.
Yeah, I agree. That's a good idea. But so, I mean, all these achievements, they are also different from each other, right? What do they have in common?
That's a good question. But I think more than even just looking at us as examples, I think we can try to look at some of the definitions sent in by our audience. And I think we can start there. Maybe that will give us a road from which we can understand it.
That's a good idea. That's a good idea. So we received more than 300 answers from the audience, and in this word cloud, we can see the words that were more common, most common amongst your definitions. And so the bigger the word, the higher the number of times it was mentioned by you.
By the way, bravo to the audience for so many answers, but you can clearly see ability and capacity are the words mentioned the most often. And I mean, they kind of mean the same thing, so we can think of them as ability. And also words like new or solve, these are some of the more common words used here. So I don't know, can we go off of creating a definition just based on these words?
Maybe, and I really like the idea that the fact that the audience chose words like ability, solve, new to define intelligence, because indeed we can make out the ability to solve a task or the ability to create something new.
I like those. What do you guys think? I think I kind of understand it, but we can definitely dig deeper. I think that's a pretty superficial understanding or definition for intelligences. So why don't we do this? Why don't we take some sample definitions sent in by the audience and maybe get a better understanding of intelligence through them?
That's a good idea. Yeah. So let's start with this one. A combination of problem solving and memory.
That's neat. I mean, that's pretty much one-liner to describe intelligence, right? And think about it. We did it all the time. We do it all the time. Even coming to this auditorium, we had to use navigatory tools. We had to use problem solving and our memory. And also, in our everyday lives, we all encounter relationship problems, and one of us is better in solving than the others, and we all know who is who. But also to show how much we use this, problem solving and memory, I'd like us to do a game. So this game requires us to use our short-term memory, and we also have some quantitative capabilities. So you mind explaining it a bit more, Anna?
Yes, and to play that, we'll invite our audience to play with us.
Yes.
So the task is very simple. I'll count down from 3, and then the 9 numbers between 1 and 9 will appear spread randomly across the screen. And then you'll have 5 seconds, and 5 seconds only, to memorize their location. After that, the numbers will be replaced by white squares, and I will ask you to guess, with Pranay, the location of numbers in numerical order. Okay? Ready?
My name is ready. Let's go.
Let's go. So, 5 seconds. And they're gone. Okay.
Yeah. I think I can go. Let's go. So the first number is here. Am I right? No? No? Wait, what? Isn't that not number 1? What is number 1? Up.
That one?
Yes, okay, cool. That's number 1.
It is number 1. Okay, thanks to the audience. Okay.
Give a hand to yourself. Okay, fine. I'm getting number 2 right. No, wait, what is number 2? This? Left? Okay, that's number 2.
Let's check. It is number 2, okay.
Oh my God, I'm bad at this. Wait, I'm flustered now. You guys tell me, which is number 3? First? Yeah, is that?
It is.
What about this? Number 4? That's 4. Okay, that's 4.
It is
wow.
4.
What is 5? This one? Cool.
Okay, then 6, 7.
What is 6 and 7? Yeah, here? What is 6? Let's go 6. 6? Okay, this is 6. Okay, what is 7? 8? That's 9 on top? Okay. 8, 9. Wow, bravo! Good job, you guys.
Good job.
I think this clearly says something about me, which is the fact that I couldn't get one answer right.
Yeah, maybe. Well, I think you did pretty good. And, however, I think that you did fairly good. But
really?
You did pretty good as well. But let's see how you fare against our distant cousins.
Okay.
And so this chimpanzee here is called Ayumu. And actually, he performed this exact same task as part of an experiment to study working memory. So let's see his performance.
Wait, hold on. This video is sped up, right?
It's not. Not at all.
Don't joke with me. Like, you're telling me that it's displayed for so small and it's figuring all of them out, right?
It's true. He actually solved the task more accurately, and he even saw the numbers for less than a second.
Wow. That's Please say something to save my embarrassment.
I'll just say, like, don't be too hard on yourself, because actually, Ayumu went head-to-head against university students, and he solved the task more accurately and faster.
Well, clearly, Ayumu did not get a PhD degree. So you're telling me Ayumu is smarter than the average human?
Well, I don't think we can say that, but we can say that chimps are probably better than humans when memorizing visual patterns and recalling them quickly. And this makes sense because this can be quite useful in their natural habitat, for instance, to remind quickly the location of predators or fruits in a tree.
You're a good friend, Anna. You saved me some embarrassment by giving a rational explanation.
You're welcome.
But another thing which I really like the chimp did was it saw those numbers and it decided to click on them. So it's, in a sense, you can say it's connecting the dots. And I think that's a very comprehensive way of understanding intelligence, which is why I like this definition, to be able to connect the dots. It's pretty simple, too. I like one-line answers.
It is. It's simple, and we do that, too, right? I mean, we sometimes solve certain mysteries rather like a detective, putting the clues of the puzzle together. And we do that as scientists as well, right? That's our work, putting the puzzle together in hopes of getting a better understanding of the environment we live in.
And definitely, we do try. But also, I think this can be thought of as an analogy. Think about it. Let's go back to the example of navigation. We use road system to connect one building to another, or rather, one city to another. And that requires a form of intelligence, too. So if you look about this map, this is the Iberian Peninsula, which I guess you guys will be more familiar about it than I am. But there's a tons of road networks here connecting from major city hubs to the major city hubs, right? And the thing is, this is very efficient planning. And this took engineers and planners decades of time to come up with this efficient roadmap. But a single-celled organism can do this in a couple of days. It's known as Physarum polycephalum. Now, I'm pretty sure I did not do the name justice, so I'll just say the common name, the slime mold. So the slime mold is placed in the center, and the white spots you see here are its nutrient source. So the slime mold, in a sense, is devising an efficient way to go to its different nutrient sources, and in the byproduct of that is, it's able to create a more efficient roadmap than the ones we have devised over decades of planning. Now, granted, the slime mold is only doing this because it wants to go to its nutrients, but that shows you some sense of intelligence right there.
Yes, it's amazing. And there are also other definitions that are a bit different and I also liked.
Such as?
Such as this one, capacidade de adaptação.
The ability to adapt. I'm trying to learn Portuguese. So, it's true, we have to. But that actually is pretty true when you think about intelligence. And I also saw another definition which was pretty similar in more scientific terms, which was basically the interpretation of stimuli to adapt to and adapt its responses to an ever-changing environment. In a nutshell, you have to constantly keep adapting in order to survive.
And indeed, interpreting stimuli and adapt our responses to the environment is a fundamental concept on the way we live, right? It's a basic survival skill. If we don't constantly adapt our responses to the environment, for instance, when crossing the road, there is a high chance we get hit by a bus.
I don't think that's plausible. But point is, when you think about adaptation, a lot of examples come into our mind. But I specifically found this one example, which we'll be showing you right now, pretty incredible. Now, let me provide you some context. The example I'm talking about is known as the lyrebird. The lyrebird has this amazing ability to mimic any sounds it can hear.
He actually can mimic the sound of more than 20 other birds, and he does that in such a convincing way that even the birds from the other species are fooled.
But in forms of adaptation, the lyrebird has, how can I say this? It's done this in a very strange form of adaptation. It is mimicking the noises, which are, in a sense, the cause of its habitat's destruction. Just take a listen. That's amazing. And it actually also sends a powerful message, the fact that how much we humans have encroached into their habitat, that our artificial sounds are the most common noises for them to mimic them. But also, just in terms of mimicry, that was beautiful.
Yes, and I was also amazed by how well he could mimic artificial sounds, almost like a digital recording.
Exactly. I mean, to be able to listen to something and to be able to replicate it, that does require some form of intelligence.
It does. Well, let's move forward. Here's another definition I liked. Extract knowledge from ingredients and act with a purpose, which may translate into trying to infer something from pre-existent information, right? And we also do this every day. We make inferences, predictions about the future when reading, when having a dialogue, or, for instance, when driving, right? We do need to constantly predict what the other cars will do next based on their positions.
True. And in a more natural habitat, that's the similar relationship of a predator and prey. Both have to anticipate when and where those two objects are going to be and act accordingly. Now, this brings us to an example which I found very curious, because this example is that of a fish, which is basically hunting down an insect known as the archerfish. Now, it does not have a bow and arrow, but it does have the capability to shoot out water and hit the insect right there on the leaf. So, this fish, just based on the location of that insect, was able to infer the direction of the water it has to spit out, the speed, and also the angle. And that inference, just based on the location, is something, again, can be seen in many different examples across. But I just thought this was pretty awesome to show.
It is. And there is one last definition that we would like to underline.
Go ahead.
This one, capacity to create. Take, for instance, art, right? You really need to be a genius to compose like Miles Davis or Beethoven, or even, as you said at the beginning, right, to the cities we built, architecture with proper planning. That's really a skill set that is born out of trying to create something new.
Agreed. And if we go back to our animal roots, we can see this in insects too. I mean, most of you already know about the bees and ants, how they build these complicated structures as architecture. And just to focus on bees for a moment here, because if you look at the bees, they basically have this hive, beehive, and all the cells in the beehive are constructed in this one particular shape. And this shape is optimized in a way to have the most amount of volume of honey and the least amount of wax used, which is the hexagonal shape.
What do you mean?
And, okay, what I mean by that is it optimizes that. So forget about the hexagons, right? Think about any other shape. Circles, or I don't know, pentagons. They don't necessarily fit well. There are some gaps you can see here. You can see here the gaps here and there. But, if you look at these shapes like hexagon, which you just saw, or the triangles, or maybe even rectangles, that actually fits well together. Oh, we just went away.
You're there.
Because the slide was no, you're focusing too much on shapes. We don't want geometry lessons. But here's what happened. We can use both of them fit well together, but at the same time, hexagons are based on papers and engineering descriptions. They require the least amount of wax, while at the same time storing most amount of honey. And that served as an evolutionary purpose by which the bees have conserved this particular shape. And I think that's marvelous.
It is. Well, so far, we've shown you a number of intelligent species, intelligent animals. And before this event, we asked you, members of the audience, what is the most rudimentary form of intelligence? Let's check your answers.
There you go. Clearly, bacteria is a lot. But at the same time, you also see different people have voted for different organisms. And I like the fact that humans are, in some cases, the most rudimentary form of intelligence. But technically, there's no wrong answer here. Because, like we just showed you, we have these different examples of chimpanzees having better short-term memory, insects creating these marvelous architectures, and also slime mold building a more efficient network. So I hope that gives you context to what you guys have done in this answer.
Yes, and so in a way, you guys got there at the beginning, and we hope, indeed, we gave you some context.
And with that context, I hope we can frame or have a better understanding of intelligence. So intelligence is diverse and is context-specific. So the question is not about how complicated or how complex intelligence is, but rather, for a given task, is it able to solve it efficiently in that context? That is a better way of understanding intelligence.
Yes, but you know what? I do think that we humans are often too focused in our own intelligence as the only form, and maybe if we were a bit more humble, we would be able to more easily recognize that other animals are superior in solving particular problems, and maybe be more prone to learn with them.
I agree. And a guy with a lot of humility, which is what a person with a lot of humility would say, I completely agree with that. That's how intelligence should be looked at. But I think one of the things we can do is we looked at a lot of the principles by showing these examples, right? So let's look at some of the principles we covered when we talk about intelligence. Some of them include problem solving, memory, pattern recognition, adaptation, inference, and creation. Now, we're not saying that these are the only way you can be intelligent, but rather, these are some important markers or principles when you think about intelligence or how to define intelligence.
Yes, but one thing that we humans excel at is in our ability to use different aspects of intelligence in a wide range of contexts. That was how we spread across the globe. We built cities, we built rockets, we built smartphones, we created art, right?
Yeah.
And, well, artificial, we said at the beginning, was the ability, or was something that was created by humans, right?
Yes, it was. And that actually brings us to why we are here tonight. So we humans have done something remarkable. We have created new forms of intelligence, artificial intelligence. And that's what we'll be exploring tonight.
Now, to help us understanding the rise of the algorithm, we will call upon the stage an in-house researcher. He received his PhD in neuroscience at the Champalimaud Foundation, and then he worked at the MIT studying artificial intelligence algorithms that better approximate human intelligence. Now he is fortunately back, and he is co-leading the digital surgery lab here at the Champalimaud Clinical Center, where he and his team are developing an innovative medical device to allow surgeons to identify tumors through patient skin, combining artificial intelligence and augmented reality.
So, ladies and gentlemen, to understand the rise of the algorithm, please welcome Tiago.
Well, thank you so much, Anna and Pranay, for this very engaging conversation, and good evening, everyone. So as the title of my talk says, tonight we're going to explore the rise of the algorithm. In other words, we're going to embark on a journey through the history of artificial intelligence. We will explore how early developments into this field have shaped AI into the pivotal force that modern technology is today, with a wide array of applications, from automating repetitive tasks in factories to algorithms that can generate images, text, and speech. One of those algorithms is the one we're actually seeing here. So this video is the output of a latent blending model, which was developed by the Lunarim team, which is a team of researchers working here at the Champalimaud Foundation. While this particular algorithm is relatively new, the core ideas that it uses to generate these beautiful images are actually quite old, and they have been evolved through decades of research, and that's exactly what we're going to explore tonight. So well, let's start again with the question of what is artificial intelligence. We just heard Pranay and Anna debate about intelligence. Well, I'll just borrow a definition from the European Commission that says that artificial intelligence are systems that display intelligent behavior by analyzing their environment and taking actions with some degree of autonomy to achieve specific goals. And luckily for us, we just heard Anna and Pranay talk about many different types of intelligent behaviors, and we saw how they can assume many different forms and that they are context-specific. So intelligence behaviors emerge to solve specific tasks. And artificial intelligence, in that sense, is like biological intelligence. There are many different types of artificial intelligence algorithms that solve a wide variety of tasks. So as a field, artificial intelligence is generally considered to have been established in 1956 during the Dartmouth workshop, where a large number of world-leading mathematicians and scientists met to clarify and develop ideas about thinking machines. Here in this picture, you can see many of the participants in the workshop. I would just like to point some Claude Shannon, the creator of information theory. John McCarthy was the person who actually gave rise to the name of artificial intelligence, and Marvin Minsky, a very influential, one of the most influential AI researchers from the past century. So, as you can see, we have here theorists, mathematicians, we have scientists, neuroscientists. So artificial intelligence did not appear in a vacuum. In fact, it its goal to understand and replicate intelligence, it actually borrowed from many different fields, many existing academic disciplines. And so since this beginning, the quest of AI has been deeply intertwined with our desire to understand and replicate intelligence, and therefore it's not a surprise that neuroscience, which is the study of how brains process information, make decisions and learn, has been an invaluable field of research to inspire early developments and even current developments in AI. Another equally important field is the field of psychology that studies cognitive processes, and particularly the study of learning and decision-making has also gave rise to many profound applications that have had an impact in AI. Another area of knowledge, linguistics, that deals with the study of languages and symbolic reasoning, has also been used by AI to develop some language models. Cybernetics, particularly Norman Winner's work on self-control and feedback signals and self-regulation, has also influenced how AI systems may adapt and evolve. We have information theory that deals with how information is processed and how data is encoded, has also been critical in shaping ideas in artificial intelligence. Computational theory, providing a framework to understand and study computation and also know its potential and limits. And then finally, philosophy, particularly its study of the mind and consciousness, has provided a unique perspective into the study of the nature of intelligence. So, and again, to go back to that idea that AI is very diverse, there's many different applications of AI, and as I said, different tasks require different AI algorithms, but in broad terms, we can divide AI into very large approaches. So the first one, called traditional AI, has to do with algorithms that do not learn. They're called the non-machine learning AI, and they operate on explicit rules and logic. The systems, like early chess programs, are based on a comprehensive set of instructions that are followed, that are defined by programs, and then once these instructions are followed, these algorithms solve particular tasks. Now, there are multiple applications that employ these algorithms, ranging from industries such as medicine, law, finance, mapping, chatbots, and gaming. And there's many different types of systems. They come in different flavors and names, expert systems, search algorithms that have to do with pathfinding in maps and optimization problems, knowledge-based systems, symbolic AI, as we've already seen, and game AI. Now, a very different approach to traditional AI has been the one of machine learning. Now, machine learning actually does not explicitly program how these algorithms would behave. In fact, it just defines frameworks where algorithms can actually learn from data and adapt to the problem that they're solving. So as I mentioned, they're not explicitly programmed in the strategy that they adopt to solve a particular task, but they actually learn that strategy when encountering data. And like the previous ones, there are many, many different types of machine learning algorithms in how they learn from data, in the types of tasks that they solve, and in the types of algorithms that they're implemented. And so it's not possible in the scope of this talk to go through all of them. However, there's one type of family of algorithms, which are the artificial neural networks, that I would like to dive a little bit deeper and share some core ideas with you tonight. So a landmark paper in the field of, particularly in artificial neural networks, was the pioneering work of McCulloch and Pitts. This is a paper that came out in 1943, and here the authors were inspired by biological neurons in the brain, and they conceptualized a simple model that later would become the cornerstone of artificial intelligence, and that's the artificial neural network. So to understand first how an artificial neural network works, maybe it's a good idea to just take a moment and understand how an actual biological neuron works. So the neuron is the basic building block of the nervous system, and you can think of a neuron as a mini processor. It receives a set of inputs, and these inputs can be several thousands, and then it combines the inputs, and depending on the pattern of inputs that it receives, it may or may not propagate a signal that then is transmitted to downstream neurons. like the biological neuron, the artificial neuron is, in this case now, is a mathematical model, but it shares many commonalities. So it attempts to simulate this behavior of biological neurons, and it also receives many inputs, which we can also call, features. We just like to complicate terminology, so now let's just call inputs features. So these features can have different levels of intensity, as you can see here by the size of these circles. Like in this case, this input here is providing a stronger signal to the neuron. Now, the neuron does not weight all the inputs equally. Some inputs may actually be more relevant for the neuron. And we capture this phenomena by this concept of weights. So here you can see that these arrows have different thicknesses, and this means that the thicker arrows means that the neuron actually tends to wave more particular inputs than others. Now the neuron is going to combine these inputs, multiply by their weights, it's going to do some processing, and that processing usually involves applying a mathematical operator that can assume many forms, but the very popular one is just a binary choice. It compares the inputs with a certain threshold. If the inputs are above that threshold, then it provides a certain answer, in this case an S. If it's below that threshold, the answer would be no. And so it does a certain computation, it combines the inputs, and then it provides a decision. In this case of a binary classification, the decision can be either yes or no. But there are other flavors, of these decisions, and they allow the neuron not only, in some cases, to give a binary decision, but it can also give some probability value that is not just discrete, but can actually be analog. Now, this is very abstract, so maybe let's consider a particular problem. So let's think about an artificial neuron that detects whether a fruit is a watermelon. So I don't know about you, but I really like watermelons. And so our simple model just receives a fruit and then detects whether this fruit is a watermelon or not. So we have here our artificial neuron. And now, what are the features? Well, we can think about the features for the watermelon, in this case, our watermelon detector, as the color of the inside of the fruit, the weight of the fruit, and the size of the fruit. And so we have our artificial neuron. It has some weights for all of these inputs. And so let's say now we provide a fruit to our watermelon detector, and the fruit has an orange color. It weighs 50 grams, and it has 3 centimeters. And so the neuron is going to compute these inputs, compare with the threshold, and provides the right answer that, no, this fruit is not a watermelon. In fact, it's a loquat. In Portuguese, we call this fruit as nespera. So this is how basically an artificial neuron works. Now, let's now give another fruit to the neuron. So in this case, the fruit is red. It weighs 8 kilos, and it has 30 centimeters. The neuron will now combine the inputs and provide the answer that, yes, in this case, we're in the presence of a watermelon. So now let's take a pause at this moment. We've gone through a lot. I tried to hide all the mathematics to try to make this a bit more engaging, but let's recapitulate what the artificial neuron is, because this is really the basic block of modern AI. So the artificial neuron, as we saw, receives multiple inputs that we also can call them features. It multiplies each input by its importance, the weight, and then it combines the inputs to make a decision. And this decision can be a yes or no, or can also be a probability. So what I described, there's something missing here, right? This looks like one of those traditional AI systems that were just, using some predetermined logic. These weights and threshold values are all predetermined. So something is missing here, right? And there's only one thing missing. So do you have any idea what is missing in our model? Learning, exactly. So we just need to add a very simple component to our system, which is learning. So now let's do that. And in fact, this was done by Rosenblatt in 1958. It implemented a new algorithm, which he called a perceptron. Now, don't be intimidated by the neuron. Perceptron is just like an artificial neuron that now can do something very important, which is learn. It can learn from its errors in a process that is called training. So when a perceptron is going to go through some examples, it's going to process them, And then when it makes a mistake, it will realize that it made a mistake, and it will update some of its parameters. The parameters are the weights and the threshold to compensate for the mistake such that in the future, the neuron does not make that mistake again. So to understand how this neuron, the perception, can train, let's go over our watermelon detector again. So we have our three features, the color, the weight, and the size. And now we're going to give a set of fruits to our model, and the model is going to learn. Okay, so let's go for the first fruit. Again, this is the example that I used. It's a low quad, so it's orange. It's relatively light and small. It's not a watermelon. So you see, it will process these inputs, and it will give the right answer that it's not a watermelon. Now we're going to give another fruit. In this case, it's a banana. So it's yellow, it's a little bit heavier, it's a little bit larger. It should not be a watermelon, but our model was not initialized correctly, and it actually thought it was a watermelon. This is clearly wrong, and so now our model will learn from this mistake, and will learn by adapting the weights. So it's going to give more importance to the weight, remove importance to the size, for example, and it's going to shift the threshold. Now we go over another example. In this case, it is a watermelon. It's red, it's heavy, it should be a watermelon, but for some reason, our model thinks it's not a watermelon. And so there's another mistake. There's going to be another update of the weights, another update of the threshold, and the model learned a little bit more. And now we go through another fruit, which is a watermelon, and now our algorithm correctly says that it's a watermelon. And now we go through a tomato, it's not a watermelon, an orange, it's not a watermelon, so you can say that our perceptron actually learned to classify watermelons. So this is a very simple algorithm, but actually was able to learn to classify one fruit from others. So again, let's recapitulate what we have seen. This is just what we had before. The perceptron is just like a single artificial neuron, but now it can learn from mistakes while processing data, and it does this by adjusting its internal parameters. Okay, so now, if you're following me into this moment, congratulations, because you know basically the key concepts of artificial intelligence. Artificial intelligence, modern artificial intelligence algorithms are basically just a lot of these perceptrons all bundled together, forming very large networks with millions of the perceptrons organized in multiple layers. So this is really a core building block of artificial intelligence. Now, this is a very simple algorithm, and there's several things that it cannot do. When I learned about the perceptron, there was one thing, even though I understand the algorithm, I understand what it's doing, but there was one question that puzzled me. It is, what is the algorithm actually learning? I know it learns by adjusting the parameters, but what is it learning? And to answer this question, we need to look at a concept that is the concept of representations. Now, representations are sort of like analogous to human mental models. They are the ways that systems process information. And so representations can be more or less complex. And the complexity of the representations is critical to allow systems to solve a task. So to understand what representations are, let's go back to our example of the watermelon. So now we want to build, again, a classifier, but let's make it simpler. Let's ignore all other fruits, and now we just want to discriminate between watermelons and melons. So, as I mentioned, a representation is a way to represent information. It's obvious by the name. And so, one possible way to represent fruits is by considering some of their properties. So, let's assume a pair of properties, in this case, the weight and their size. And now we're going to look at many examples of fruits. So we take the first one, we measure the fruit, we measure the weight, we measure the size, and we basically put a circle in this diagram. Now, this circle represents one example fruit, so one fruit that we're considering. Now, we do this for many, many fruits, and we basically populate this graph. So, okay, since we know, if we know a priori what the fruits are, we can now just color code them. And we can see, we color coded according to the color on the inside, Watermelons are red, melons are green, and you can see that this representation of watermelons and melons, actually, it has some information. It's not perfect, but watermelons tend to be heavier and larger, and so they kind of like accumulate here. And melons tend to be a little bit smaller and lighter, and they're here. So, we could potentially sort of discriminate between the two, but there's this region here in the center where they're kind of like mixed, where watermelons and melons, if we just look from these two features, they're very hard to distinguish from one from another. So do you have any idea where we can, create a representation that may be better to help us discriminate between these two fruits? Any ideas? It's kind of in the slide. The color, exactly. So the color is another property of the fruit. So instead of, let's say, the weight, let's remove the weight and let's replace the weight by the color. Now we can see, if this color is just the difference between the amount of red and green, we can see now that all the watermelons cluster here, all the melons cluster here, and now we can clearly separate all of the example watermelons from all of the example melons. And this may seem very simple, but this is a very, nuanced, property of AI and artificial neural networks. Is that when they are learning, what they actually are learning is that they're learning better ways to represent their information. They're learning ways to represent their data in a way that is easier to actually classify and solve the task at hand. So this is really important, and I want to emphasize here that during training, what a neural network is doing is learning a good representation of the features for a given task. And this for a given task is very important because a representation makes sense in the context of a task. And so some representations may be better for solving some tasks, other representations for others. And so when we're training a neural network to solve a particular task, it's actually learning how to represent the features in a way that is useful for solving the task. So far we've looked at one single neuron perceptron. We've seen that this model can learn to solve simple tests. It can actually learn to represent information in these very simple representations. But its capacity to solve problems is very, very limited. We cannot do more interesting tasks. And so researchers, inspired by the complexity of circuits in the brain, they also attempted to scale up this simple model to replicate the complexity of biological neural networks. So it became apparent that AI needed neural networks with many more neurons organized in multiple layers. And so what we have here is, it's still a very relatively simple neural network, but now it's considerably larger than the one we've seen before. So here we have a neural network that has 7 inputs or 7 features. It can produce 9 outputs, and it has 5 middle layers, also known as intermediate layers. Now, if we think back about our example with the fruits, this could be a model that would discriminate between 9 different types of fruits by accepting 7 different properties of fruits. Now, in addition to the 3 we've seen before, we can now look at whether the fruit has seeds or not, the sweetness of the fruit, whether it grows on trees, and the season of the year where it grows. So this type of model can now learn more complex representations and can solve more complex tasks. However, when researchers first started implementing these models and trying to train them to solve tasks, they quickly encountered some technical difficulties. And that difficulty is, as we have seen, that the model actually learns when it makes a mistake, and then it updates the parameters for each neuron to kind of compensate for the mistake. But in order to do that, it needs to know the outcome, and it needs to kind of know how its decision contributed to the outcome. So there's a term here in neural networks which is called the backpropagation of errors, because if we want to update the parameters, let's say, of this neuron here, we need to backpropagate the errors at this layer all the way to this neuron. And this was very challenging to implement and to train when these models were first proposed in the 60s and 70s. So with the perceptron we had here in the late 1950s, and the answer to this problem actually appeared much later. to be honest, the first solution actually came in 1970, but it went largely unnoticed, and only in 1986, David Rumelart popularized what is now known as the chain rule, which is a very simple mathematical trick that was used to train these models. And this allowed now an efficient way to actually update the parameters of this neuron by knowing the outputs here, backpropagating the errors in a way that is efficient to implement computationally. So, as I mentioned, this happened much later, so in the 80s, and during the 70s, artificial neural networks were facing many challenges. They were not very efficient in solving problems, and so there was a paradigm shift in AI where machine learning approaches kind of like felt out of popularity, and that's when traditional AI systems actually took the front stage. And as I already mentioned, these systems were used in a wide variety of industries, ranging from medicine to finance. And a very notorious example was IBM's Deep Blue, the chess program that beat Garry Kasparov in 1997. And this was an AI system that was basically, combined, experts. It had sort of like a search algorithm and knowledge, and also could do some symbolic calculation. So that's basically Deep Blue was a traditional AI algorithm. So at the same time that this was happening, there was a very interesting debate in the field. So there were some people that were saying, if we really want to build models that can emulate human-level intelligence and solve tasks in a way that humans do, we need to go back to the artificial neural networks. We need to find ways to make them work because they more closely replicate how animals learn and solve tasks. Other experts in the field were actually saying, no, these models are, not only they're too hard to train, but actually I don't really understand how they work. They're kind of like sort of black magic because you just give them data and they learn something. I prefer to build models that I can design the rules, I can predict how the model behaves. It gives me more confidence about the outputs of the models. And so there were many people working in symbolic AI. And there was this debate between the two approaches that lasted from several decades. As I mentioned, most of the applications in this time were coming from symbolic AI, but that doesn't mean that research in connectionism or artificial neural networks actually stopped. In fact, during the 80s and 90s, these were periods where critical research took place that actually enabled the type of applications we're seeing today. So in 1980, in an influential paper by Fukushima, he proposed the concept of convolutional neural networks that today form the backbone of all image or most image recognition, image segmentation algorithms, and also are in generative image generation algorithms. Linearized self-attention was proposed by Schmidt-Huber in 1992, and this is basically, nowadays, this type of algorithms are called transformers, and the transformers are the T in GPT, in ChatGPT. So the core concepts that allow ChatGPT to work actually predate, over 3 decades. And a very other important algorithm, the long short-term memory, or LSTMs, which are a type of recurrent neural networks, was also developed in the same decade by Ockreiter. So it's very interesting to see that during this period where artificial neural networks were actually not being that widely used in applications, there was fundamental research that was being done that allowed applications to be developed several decades later. Now, all of these require, are so important that we should explore in more detail, but we don't have the time to do that tonight. So I will just focus on convolutional neural networks because they're also very visually, they're easy to look at, and also that's the area where I have most of my work experience. So the neocognitron, which was this model that was proposed by Fukushima. It's very interesting to read this paper because this is a paper in machine learning, in artificial intelligence, and there's multiple references to neuroscience and to how the visual system works. In fact, one of the core concepts of the neocognitron is this convolution operation that explains how neurons in early layers, they look at specific areas in the image and they can identify small patterns. And this is very similar to how our eyes and our primary visual cortex function. So there was a lot of inspiration from neuroscience ideas that were distilled into this model. Another one is the use of many layers, and as this model processes information, these representations that we have just seen become increasingly more complex in a similar way to how information is processed in the visual brain. So although these models were not being used in a lot of applications, they were being used in some. And so what I'm showing here is some examples of MNIST. MNIST is a data set that comprises handwritten digits from 0 to 9. And this type of models could actually solve that task. So this is a simple classifier. We have 10 classes, and a model would see this digit and then would say, this is a 0, this is a 1, this is a 2. This for us is trivial, but for algorithms up to this moment, this was actually a complex task. And this type of algorithms were actually used by the post offices to recognize the zip codes in mail. Now, this is a real-world problem, but it's a relatively simple real-world problem. And there were still challenges, as we've seen, to using artificial neural networks in the wild. So, and the reason for that there were several limitations, as we've seen, computational limitations, and some, and then we'll see another one. So, regarding the computational limitations, there was a major technological breakthrough that happened in the late 2000s. So GPUs are it's a graphic processing unit. This type of hardware had been done for many decades. They were originally used to play video games and develop other type of graphical applications. But in the 2000s, researchers realized that were actually very useful to train and to deploy this type of artificial neural networks. And in fact, when we look here, starting in 2010, there's really, the distance between the compute power of GPUs and traditional CPUs just grow, many orders of magnitude. And around today, GPUs for processing this type of applications, they're about 1,000 times better than traditional CPUs. So this was one, addressing the computational, the technical and computational limitations of artificial neural networks was largely addressed by GPUs. Another one was the availability of data. As we've seen with our fruit watermelon detector, in order to train this model, the model needs to go through many examples of data, in our case, examples of fruits. Now, if we want to build a model that can detect images, we need to present many images, and those images need to be labeled. And this was something that simply was not available. However, with the advent of the internet and with the first social networks, and I think at this time was the one that was particularly important to establish ImageNet was Flickr for the non-Gen Z people in the audience. So this was an early social network where people uploaded images, like today's Instagram. And ImageNet comprised millions of images belonging to 1,000 different classes. So we just saw, our fruit example, we had 9 different classes of fruit. ImageNet has 1,000 different classes of many objects, animals. I kind of think that half of them are just basically dog breeds, because really there's dozens of dog breeds on ImageNet, but still it was the availability of this data that allowed an efficient way, and also paired with the GPUs, that we were now able to train artificial neural networks to solving complex problems. And the problem at hand may seem trivial for us. You look at an image and you say, this is a dog or this is a cat, but this problem is actually is incredibly complex. If you think of an image as having, let's say, 1 million pixels, each pixel is actually a feature. And when we think about this, this becomes a highly dimensional problem that is very difficult to implement using the type of perceptions that we've seen before. And so the first model to really make a breakthrough in this problem of object recognition was a model that is named AlexNet from Alex Krzywski, the first author of this paper. And it came out just 2 years after the ImageNet. ImageNet also provided something very important, which was not only giving the data to train the models, but also giving a benchmark to evaluate the models. There was a competition running every year that evaluated how good the models were in solving that task. And in 2012, when AlexNet was developed and ran to this model, it just blew away all the other competition. There was really a qualitative increase in performance from this type of models. Again, these are convolutional neural networks to other models that employed other AI strategies. And so now we're coming to the end of my talk, and I would kind of like to say that we've sort of like come full circle now, because we've seen how many concepts in artificial neural networks, from the concept of the artificial neuron to convolutions to multiple layers, have been inspired by neuroscience. Recently, neuroscientists have been using this type of models to actually understand how the brain works. And this is work that was done at the lab of James DiCarlo at MIT, where I did my postdoc work. And in this paper, the authors used a convolutional neural network as a way to understand how different areas in the visual system of the monkey were building these representations of different stimuli. And they were able to actually predict how neurons in the monkey would respond to novel images that they are not shown to train these models. And work that I was personally involved in, this was a model that I developed. We're now continuing developing this type of models, but more closely replicating the type of processing that is happening in the brain to now implement some type of computations that we know that our brain does in these artificial neural networks in order to make these models better. So these models still suffer from many limitations. They do not generalize to new images. They can be attacked. These are some interesting problems, still open problems in AI, and we realize that if we more closely mimic actually the brain, we actually develop a model that is better than if we just use traditional machine learning approaches. And with this, I would like to conclude this talk. So I would just go over what we went through a lot of information. I don't expect you to memorize everything, but there are some key takeaway messages that I think would be important for you to take home tonight. And these are that artificial intelligence is like biological intelligence in the sense that it's very diverse. There are many different types of algorithms, and they can solve many different types of problems and tasks. AI is a highly interdisciplinary research field. We've seen how psychology, linguistics, even philosophy and information theory contribute to AI, but a very important one and close to my heart is neuroscience. AI has a very long and rich history. Even though AI is becoming a buzzword and there are many applications, actually we've seen that its history goes back many, many decades. And in fact, there were core concepts in current algorithms in AI. They were actually created several decades ago. And then finally, this idea that all that we've seen coming up in the last years, they build on research that was done several decades ago, but really the two critical ideas that enabled the appearance of these powerful models as being the increase in computational power and the availability of large data sets that didn't exist prior to the internet. And with that, I will conclude. I would thank you for your audience and our initiative for organizing this event. I will be outside if you would like to talk with me to answer any questions, and we can talk about these concepts in a more informal manner. Thank you.
Well, again, round of applause for Tiago, guys. Like, he really did say a lot. Thank you, Tiago.
Thank you, Tiago. Thank you so much for this talk, taking us from the birth of AI to the powerful systems driving the current AI revolution.
Yeah, so Tiago kind of gave us a perspective on how, and deep neural networks, or on how the current AI works, right? So we thought we can use some of the concepts we learned about intelligence and some concepts Tiago laid out, and use our current neural networks to build our own AI creation of sorts. So I promised you guys we'll introduce you to Leslie. So here I am introducing to Leslie. Hi, Leslie.
Hi, Leslie. Good evening.
Good evening, Pranay and Anna. It's a pleasure to be here with both of you. I'm excited to share some insights into the fascinating world of AI.
Cool, right? That's Leslie, our in-house AI creation. And it's pretty simple. Like Tiago said, we have a bunch of these different neural networks and neural architecture right now, artificial neural networks. So we thought, why don't we use our own to kind of outline the history of AI, or rather the major milestones of AI through Leslie. So before we get into all that, we kind of asked you a question to kind of understand what you guys thought. And since Tiago gave a history lesson, let's see. What was the question again? What did we ask?
Yes, so before this event, we asked you, members of the audience, when did AI start impacting society? So let's check your answers.
Again, pretty varied.
Okay, so I see that a lot of people said it was during the 50s, but also a lot of people said it was during the 2000s. So let's maybe ask Leslie. Leslie, what would your answer be?
That's an interesting divide in opinion. My answer would lean towards the earlier estimation. AI began influencing society as far back as the 1950s and 1960s. This period marked a shift from theoretical AI to practical applications, like the creation of ELIZA in the mid-1960s, one of the first programs attempting human-like conversation. These early developments laid the groundwork for the myriad of AI applications we see today.
So just to be clear, Leslie, so ELIZA must be like a grandparent, right? Can you elaborate a bit more about ELIZA, Leslie?
That's a fun comparison, Pranay. Developed at MIT, ELIZA was a groundbreaking early chatbot. Although it was basic, ELIZA demonstrated the potential for machines to interact with human language, sparking further research in chatbots and virtual assistants. Here's a short video about ELIZA.
Just like a therapist, people could come and talk to the machine by typing in their problems. Weizenbaum called the program ELIZA. He modelled it on a real psychotherapist called Carl Rogers, who was famous for simply repeating back to the patient what they had just said. That is what ELIZA did. The patient sat in front of the screen and typed in what they were feeling, and the program repeated it back to them, often in the form of a question.
Men are all alike.
In what way?
They're always bugging us about something or other.
Can you think of a specific example?
Well, my boyfriend made me come here.
Your boyfriend made you come here.
He says I'm depressed much of the time.
I'm sorry to hear that you're depressed.
It's true. I am unhappy.
Do you think coming here will help you not to be unhappy?
Well, I need some help. That much seems certain.
One of the first people to use ELIZA was Weizenbaum's secretary, and her reaction was something that he had not predicted at all.
And I asked her to my office and sat her down at the keyboard, and then she began to type. And of course, I looked over her shoulder to make sure that everything was operating properly. After 2 or 3 interchanges with the machine, she turned to me and she said, "Would you mind leaving the room, please?"
And yet she knew, as Weizenbaum did, that ELIZA didn't understand a single word that was being typed into it.
It's been 60 years, and men are still alike.
Well, I don't know about that, but it's fascinating. And, well, I work in psychiatry, and I found so interesting that people were so eager to share so much with ELIZA, which is just simple software running on a computer. I mean, usually people only tend to share such personal things with other humans or other animals, right? And this takes us to another important concept in AI, which is robotics. And some people even argue that for AI truly emerge, it will need to have a body of its own. So, well, Leslie, what do you think? What were the first steps of AI in robotics?
Absolutely, Anna. ELIZA, like myself, was indeed just software running on a computer. The integration of AI with robotics, which combines software and physical form, began making significant strides with Shaky the robot in the late 1960s. Shaky, developed by the Stanford Research Institute, was the first robot that could perceive its environment, make decisions, and navigate on its own. It had cameras and sensors to interpret its surroundings and used basic AI algorithms for problem solving and movement. Here's a video of Shaky.
At SRI, we are experimenting with a mobile robot. We call him Shaky. Our goal is to give Shaky some of the abilities associated with intelligence, abilities like planning and learning. Even though the tasks we give Shaky seem quite simple, the programs needed to plan and coordinate his activities are complex. The main purpose of our research is to learn how to design these programs so that robots can be employed in a variety of tasks, ranging from space exploration to industrial automation. Shaky operates in this experimental environment of rooms, doorways, and simple objects. The top lens belongs to Shaky's television camera. He uses it to obtain visual information about his own location or about other objects. Shaky uses these feelers, or cat whiskers, to tell him if he has bumped into anything. He can push objects with this push bar. Shaky communicates with the computer over a radio link. The GoTo program plans a route by first computing whether any obstacles lie on a direct path. If so, points near the obstacle are set up as sub-goals. After Shaky computes a route, he traverses it to the goal. Our experiments with Shaky have helped us learn more about how a computer can be programmed to control a robot. Continuing research at major centers, like SRI, will someday allow intelligent robots to leave the laboratory and enter the service of man.
Two things I'd like to point out. One, the fashion choice. I don't know how many of you noticed that. And two, it is pretty unnerving, Anna, that you said that you'd like robots to have a physical body so that you can converse with them. And Shaky already kind of demonstrated that in the 1960s. Yeah. So, but technically, this is still in the realm of research, right? So why don't you ask Leslie? So Leslie, when were the first AI applications in real life?
The leap from research to real-world applications began with the advent of expert systems in the 1970s and 1980s. These systems applied AI in practical, industry-specific ways. One of the most famous early expert systems assisted doctors in diagnosing bacterial infections and recommending antibiotics. In addition, expert systems found applications in fields like finance, where they were used for loan analysis, and in oil exploration, where they helped in interpreting geological data. These systems were revolutionary because they allowed for more efficient and accurate decision-making in complex tasks, which was previously the sole domain of highly skilled professionals.
So, indeed, the first real-world applications of AI happened more or less 50 years ago. Well, any other real-world applications, Leslie, that people here can relate to?
Absolutely, Anna. A relatable example for many would be IBM's Deep Blue. In 1997, this AI-powered computer made headlines by defeating world chess champion Garry Kasparov. Deep Blue's victory was a significant event, showcasing AI's capabilities in complex strategic thinking. It brought AI into the public spotlight and demonstrated its potential beyond academic and industrial settings. Here's an interesting video of Deep Blue.
The afternoon of May 11th, 1997. Game 6, the deciding game. Deep Blue challenges Kasparov's brain with an array of 256 processors that can examine 200 million possible moves every second. They call it the brute force approach. Kasparov doesn't try, he can't try, to consider every possible move. He knows from experience what's important, and he relies on the human mind's extraordinary ability to recognize and remember patterns. The patterns of chess experience lived in Deep Blue's software too. Grandmasters had coached IBM's programmers to deepen Deep Blue's book, its library of what humans knew from experience about how to win. Deep Blue could now play as well as a grandmaster, with all the benefits of hindsight. In the early moves of Game 6, playing by its book of openings, then in the mid-game analyzing millions of possible scenarios by sheer brute force, Deep Blue has led Kasparov into making a poor move. Kasparov is rattled. He defends what he can. But it's clear that the computer will reliably do what he himself would do. And he recognizes that he has already lost. On Deep Blue's 19th move, the champion resigns. For people watching around the world, it is a slow-motion moment.
I mean, sure, funny in hindsight, but as the music encapsulates, pretty tense moment, because technically this was the first moment in human history where machine, in essence, caught up with human intelligence. But 2 points. First, that machine was specifically tasked to play chess and nothing else. It took years of training and iterations by multiple grandmasters, as mentioned, for it to actually beat Kasparov. And the second thing is, it couldn't lift a single chess piece, even if it wanted to. There's no way it could have done that. Now, that's nowhere technically close to what the AI we have right now, like the examples Tiago was talking about. But it was, or rather, a huge milestone in powering AI. So maybe, Leslie can give us a few examples. So Leslie, can you give us a few examples of how AI has been embedded in the past couple of decades?
One significant area where AI has been involved for decades is banking, particularly in fraud detection. Since the 1990s, AI has been instrumental in monitoring financial transactions to identify unusual patterns that might indicate fraud. These systems are adept at analyzing vast data sets much more quickly and accurately than humans, making them invaluable in protecting financial integrity. Beyond fraud detection, AI has also been used for credit scoring, algorithmic trading, and personalized customer service in banking.
Interesting. And what about physical tasks? Any physical tasks that you can think of?
Indeed, AI has also made strides in physical tasks, especially in manufacturing and logistics. One key area is robotic process automation, RPA, where AI-driven robots perform repetitive tasks with high precision and efficiency. Since the late 1990s, these robots have been used in assembly lines, packaging, and sorting processes, transforming the manufacturing sector by increasing productivity and reducing errors. This application of AI in performing physical routine tasks showcases its versatility and ability to adapt to various industries, as we can see in the following video.
What you're looking at behind me is the hive. We've got the grid, which is the metal structure. It's filled with product. So that product is housed within what we call totes, or these open boxes that you can see at the top of the grid. We have around 2,300 bots, and they move the stock around the warehouse so that we can pair it up with customer orders to be delivered. We have sensors underneath the bot that mean that every time it passes over one of the squares on the grid, it has a laser underneath it that can tell when it moves over that cell. So it will say, I've passed a cell, I've passed a cell, I've passed a cell. We have around 58,000 different types of individual products within the grid. We'll use the huge amounts of data that we gather to understand what customers are most likely to order and place them in the easiest to reach locations for bots. All of that combined means that we can have stock into the warehouse and out again from our suppliers into a delivery van in just 5 hours.
Wow. You know what's crazy? Just a couple of examples ago, I said, AI can't lift a single piece. Well, clearly it can. I mean, this is just, in the past 20 years, the movement from just being specific to one thing to now actually expanding into a more physical realm using robotics. And I think that's a bit unnerving because, it's potentially coming for our jobs. But you know what? Maybe we won't talk about that more right now. We're still in a fun vibe. Let's be fun. But that does beg the question, though. Are machines becoming more smarter than us, Anna?
That's an important question. And we asked that exact same question to the audience, so let's check the answers.
Clearly you all have faith in us.
Okay, so fortunately, most of you still think that humans have the upper hand. But now maybe let's ask Leslie. Well, Leslie, what do you think? Do you think you are smarter than Pranay or me?
That's a thoughtful question. While AI systems like me have advanced significantly, being smarter than humans depends on how we define intelligence. AI excels in processing vast amounts of data, recognizing patterns, and performing specific tasks with superhuman speed and accuracy. However, humans possess creativity, emotional intelligence, ethical judgment, and the ability to understand and navigate complex social contexts, qualities that AI currently cannot replicate. So while I can process information faster, I lack the depth and breadth of human understanding and experience. AI complements human intelligence. It doesn't surpass it. Remember, it's not a competition, but a collaboration between human and machine intelligence that unlocks the most potential.
Wow.
Yeah,
I mean,
wow.
I don't know about you, Anna. That last line sounded like a threat. But in a way, Leslie encapsulates what we're trying to show throughout. I hope we've been able to show throughout this whole event is the fact that, at least so far, AI has been assisting us, helping us. It's been a huge importance in like uplifting and changing our lifestyle. And for so far, at least, programs like Leslie and other AI deep neural networks have helped and assisted us in many, many ways.
Yeah, well, AI does has some advantages for sure, but we humans, well, I mean, we do amazing things, right? And we do that with bodies that work with fruit, watermelons, for instance, nuts or pastéis de nata, while training and running an AI system like Leslie consumes a lot of energy, like almost the same than a big city working. And furthermore, we humans, we evolved to live in communities. We developed emotional intelligence, we developed ethics. That was how we formed societies. And well, so far, that seems to be exclusive to humans, and I do wonder whether AI will ever reach them. So a lot of questions remain to be answered, and that is why we have some more events coming next year.
Exactly. I couldn't agree more. With a lot of things to unpack, and like Leslie pointed out, and like Anna pointed out, there are things we can actually go into, and hence, we decided to have an event about the present of AI and the future of AI. But before we conclude, before Anna and I say our closing remarks, we'd like to ask Leslie to say her closing remarks or their closing remarks. So Leslie, do you like to say anything to conclude?
Thank you, Pranay and Anna, for this enlightening conversation, and thank you to everyone here for your engagement and curiosity. As we close, I'd like to add a personal note about myself. I am an output of a large language model developed by OpenAI, ChatGPT, designed to process information and interact in a conversational manner. While I can provide insights across many topics, I operate based on data and algorithms without personal consciousness or experiences.
Wait, hold on. Stop, Leslie. Stop, Leslie. I'm sorry for interrupting you, but I just have one thing to ask of you, if you can do this. So you can continue with your closing remarks, but I'd just like to ask you to update yourself if you can, or rather, truly show the power of our current neural networks to show yourself in a different light. Can you do that, Leslie?
So, as we part ways, let's continue to be curious, informed, and engaged in the world of AI. It's a collaborative journey, and each of you plays a vital role in shaping its future. Goodbye for now, and I eagerly anticipate our next interaction.
Bye, Leslie.
Bye, Leslie.
Leslie, everybody.
Bye. You know what? I think that was the first time I said goodbye to an AI.
We better get used to it. But the interesting part is, what we've been showing you guys so far with the, everything about Leslie, it has the potential to actually look so human-like if it's possible. We've all seen that right now. It's so easily to get fooled. And that is why I think it's important to understand, there's more to talk about it. Hence, like Anna mentioned, we have a couple more events.
Yes. And so a lot of questions remain to be answered, and that is why we have 2 events coming next year, in February and April 2024, to explore the present and future of artificial intelligence.
And our hope is to answer more of these questions, and more of these rather gray area questions in those events. And also another thing we'd like to announce is MetaImmersion, which will be coming in March, and I hope to see you all guys there too. There you go. That's the MetaImmersion poster. So I started this evening off by saying many things to look forward to tonight, but I say now many things to look forward to in our future. And I really hope to see you all there. And so I'd like to conclude by saying thank you to the Champlain Foundation for their continuing support. Thanks to the technical team, without whom none of this would have been possible. And thanks to the art team, wherever we all are scattered. Thank you so much for your support, guys. And also, more than anything, thanks to you, lovely audience. You really were amazing. I hope you guys felt it was amazing. I hope you guys felt it was memorable. And thank you so much from my side.
So we have drinks outside.
Yeah.
So thank you all for coming, and see you soon.
So the drinks will make it worth it. Thank you.